Now, one of the things that we can do is we can actually look at how Coulomb barrier varies with projectile and target nucleus, and that's done on page 125, and it's actually done for two different projectiles, one of them being a proton and the other one being an alpha particle. So then we're going to look at, so we're going to plot on the abscissa Z number, atomic number. So we have Z down here. And on the other side, we're going to put in the effective Coulombic barrier, the effective ECB in million electron volts. And what we find is kind of interesting. So I'm going to use two different colors to illustrate this. Let's see if I can do this. So for instance, if we look at hydrogen, we're going to see that hydrogen, this is kind of a straight line, not a straight line, but it's a curve. Curves up sort of like this, and then down like that. So gets down to a low value, not to zero, but some low value. I'm going to make this thick enough that it'll actually show up on the board. So this is hydrogen, or actually it's a proton. If we're using that as the, if we're actually using the proton as the projectile. But something that's a little bit more interesting happens when we use an alpha particle as the projectile. Well, first of all, the energies start out higher. So they're up here. The barrier is higher. And then it's going to come down again like this. And then you notice it goes back up again. Well, what's going on here? So that's kind of an interesting phenomenon. And this is helium, or an alpha particle. So if we look here, we don't have any precise numbers here, but this is like, say, what they're saying here is, in your book, I'm going to call this 80, and then this is 60, and 40, and 20 atomic mass units. So 0 would be over here. We don't, of course, have 0, but I can't really tell, either the way I've drawn it or the way it is in the book, what Z number corresponds at this point here. This actually doesn't go all the way to 0. Let's assume maybe that this is 1 right here, and maybe this is 2. I'm not really sure exactly where this occurs, but it's kind of interesting that we have this little inflection here where, as we would have expected, the effective Coulomb barrier, at least for here, as the atomic mass goes up, the effective Coulombic barrier goes up. We've got more particles, so there's even a lot more repulsion. But down here, you'll notice that it goes up along here, but then at this one point here, it actually reaches a minimum, and then it goes back up to a more positive value when we go to a lower Z number, which, as I said, is probably hydrogen. So the question is, what actually is happening there? And although it's not explained in the book, my guess is that what this is indicating is quantum tunneling is actually taking place here. So your book talks about that a little bit, a little later on, but it's kind of analogous to the situation that you might have in a chemical reaction where you've got your reactants and perhaps your products are over here. They could even be below the reactants. We can put them down here. But there is some activation energy, some activation barrier that you have to overcome. So the reactants, the reactants, even though the products are at a lower energy, they don't spontaneously go to the products. We have to overcome this. We have to put in enough energy to reach this activation point, and then we can ride down the hill and get to the products. So I think you've all probably seen this if you've taken chemistry, that one of the things that a catalyst will do is it lowers the activation energy. It's kind of like you've got a mountain to climb. Well, let's just knock down the mountain, and then we can smoothly glide along here. Well, quantum tunneling it's not the same process. but by analogy, we can sort of get the same, we can get sort of the same effect, where we know that we would actually have to go up a little bit to get that energy. In fact, we can tunnel through here if at the quantum level this thing is able to actually tunnel through here without actually having to, we can actually overcome that energy and get to our products through that tunneling process. And I think that's what's actually happening here is quantum tunneling. So I want to go on then from there to the diagram that's actually shown on page 126. It's figure 7.3. And in this figure, you'll notice that there's a target that's shown right in the middle. And above and below the target, what we actually have is a 5x5 grid here. How well I can draw this, but we've got 1, 2, 3, 4, 1, 2, 3, 4. So I want 5 this way. I've got 5 rows and I want 5 columns. 1, 2, 3, 4, 5. Right dead center in the middle here is a target. This is what I'm trying to make. I'm trying to hit the target, but I'm actually, that is the nuclide of interest, the thing that I want to make. And on the bottom here, we've got increasing numbers of neutrons, and on the other axis, we have increasing number of protons. So this is our Z number. And so wherever we happen to be, if we add a proton, we would go up 1 box, basically. If we added a neutron, we would go to the right 1 box. If we lost a neutron, we'd go to the left 1 box. So that's how we're moving. So this is just showing you a series of reactions that you could do for any particular nuclide of interest. You'd put that right in the middle. And then you could look, for instance, if you wanted to make this, and whatever it happened to be, and you, for instance, had an element that had 1 more neutron than this did, and it had 2 more protons. So it's got 2 protons and 1 neutron more. That puts it into this box right here. So the question is, how do I get from that element back to here? And what you see in the diagram is the designation N and alpha. So it's telling you that if you're already here, if this is the element, the nuclide that you're looking at, if you add a neutron to it, which means you're going to bring it over to this box here, and then you lose an alpha particle, that's what's being emitted. So by losing an alpha particle, I have to come down 2 neutrons, and then I have to come over 2 protons, and voila, I've hit the target. And you can do that for any one of the things that's shown in here. Let's look at another one. Over here in this box, we've got T and N. So T is a triton, it's the nucleus of a tritium atom, and then that's going to emit a neutron. So what is the nucleus of a tritium atom? It's got 1 proton and 3, it's got 1 proton and 2 neutrons. So we're going to go up 1 proton, and we're going to go over 2 neutrons. That's going to put us here. And what are we emitting in that reaction? We're emitting a neutron. So we have to go back over to the left now, one neutron, and again we've hit the target. So I'm not going to go through all of these, but you can do any one of them, and you'll see that you'll always get back to the target in that way. So this is just showing you nuclear reactions leading to a particular product, which is in the center square. That's the target. And for the reaction that we were just talking about, the forming fluorine 18, which is an important radioisotope, it's actually used in positron emitting emission tomography. So because it's a positron emitter, remember that when positrons and electrons annihilate, they produce two gamma photons that are actually going to travel in directions along the same, whatever their axis happens to be. They're going to travel 180 degrees away from one another. And because of that, you can actually use a gamma camera, and it's possible to get a three-dimensional image by looking at these positrons as they move along in different ways as they annihilate along, and the gammas move in different directions. You're going to get a three-dimensional image of that. So that gives us what's known as a PET scan. But fluorine 18 is an important isotope. And on page 126, above this little chart, are 6 reactions that could be used to actually make fluorine 19. But we learned that, for instance, the reactions where more than one where more than one particle is being produced that's being emitted, such as reaction 5, where both a proton and a neutron are being emitted, those reactions are not terribly favorable because they require higher energies. And we also see that there are a number of, that is actually the first 3, involve isotopes that are not readily available. Nitrogen 15 is a rare isotope. It's something, although it's not radioactive, it occurs only to a very, very small extent in nitrogen. Oxygen 18 is also not readily available, nor is oxygen 17. So we've eliminated everything except reaction 4 and reaction 6, and either of those could be used to produce this. But one of the reasons why, when we look at this, that we would actually prefer to use reaction 4, which is the taking oxygen 18 and bombarding it with protons to get fluorine 18 plus a neutron, versus reaction 6, where we're going to use neon 20 plus a deuteron will give us the fluorine 18 plus an alpha particle. The reason the 4th reaction is preferred is because in the 6th reaction, since we're dealing with neon and it's a gas, and we can't make a compound out of it because it's a noble gas, it means that we're going to have it maybe in some kind of a tube or something, some kind of a capsule, to actually keep that neon confined. And then since it's in the gaseous state, it's really going to be mostly empty space. So in the case of the oxygen, however, which is also a gas, nevertheless it forms chemical compounds, and we can convert it into an oxide. And the thing that is suggested in the book is to just use water. So it would be not normal water, but oxygen 18 water. But if you use that as your target material, and there'd be other oxides you could use as well, then that reaction would actually be the preferred reaction. And then if you do all the calculations that are shown on page 127, massive reactants for oxygen 18 and the proton is 19.006985 atomic mass units. For the products, it's 19.009603 atomic mass units. Again, this is endergonic. The mass difference, the delta M is minus 0.002618 atomic mass units times 931.5 mevs per unit gives us a value of minus 2.44 million electron volts. The threshold energy is calculated from that and found to be 2.57 million electron volts, and the effective Coulomb barrier is 2.59 million electron volts, using the equation that's shown there. And both of them are very, very close to one another, but it's always going to be the greater of the two. In this case, it's the effective Coulomb barrier being greater than the threshold energy. That's the energy that we have to consider that we're actually going to have to overcome. So the effective Coulomb barrier is 2.59. What that's telling us is that as long as our projectile has at least 2.59 million electron volts, we've got a reasonable chance of getting a good yield for the reaction. Now, when we talk about reaction yield, it depends on a number of things, but fundamentally, for nuclear reactions, it's going to depend on, first of all, on the number of atoms of target material that we actually have, and it's also going to depend on the number of projectiles that we're going to throw at it. So that's actually going to be something that's going to be the number of projectiles that are being produced over a given period of time. And it's also going to depend on what is called the cross-section, which is a nuclear cross-section, which is discussed in on page 1, it starts on page 127 at the bottom in section 7.2. So the cross-section is really a good estimate of the probability of a reaction actually occurring. And the cross-section of any nucleus is actually, it's not exactly really proportional on the size of the nucleus. It depends on a number of things. Cross-section depends on the density of the target material that's being used. It depends on the charge, on the mass, and the velocity of the projectile that's being fired at the target. Less energy gives you, if you wind up having less energy, that gives you a greater chance of actually getting a reaction. So we don't want particles that have very, very high energy. So we find out, for instance, when we're firing neutrons at something, we don't want to take neutrons that are traveling at velocities approaching the velocity of light, a very, very fast-moving neutron. It's not likely to react to be captured by the nucleus. So if we're actually looking for neutron capture, which is actually what we are doing in nuclear reactions, where we're trying to take one isotope and convert it into another one, we want to lower the energy of the neutron down considerably. And there's a number of ways that we can do that, but we can produce what are called thermal neutrons, which actually have much lower velocities and lower energies. And we find that thermal neutrons have an energy of about 1/40th of an electron volt. So about 0.025 electron volt is a thermal neutron. We can even go to lower energies than that. Whereas a neutron that's moving at very, very high velocities could have energies in the keV or even MeV range. It's going to be much, much greater than this. So these are slow-moving neutrons. We can take neutrons that come out at very, very high velocities. For instance, even a neutron that is expelled in the reaction between, if we take, for instance, beryllium, which is 4, and I think it's 9, I don't remember, but if you do that and react it with an alpha particle, that will actually produce neutrons. So that's going to give you 0 and 1, and the other product has to be carbon 12, I guess, yeah, carbon 12. So that's going to give you carbon 12 plus. So you can take beryllium and actually put it next to something like either polonium, which is producing these alpha particles. You can irradiate it with polonium. I could probably even do it with americium, and I can produce neutrons. And the neutrons are going to be going very, very rapidly. But if I take those neutrons and then pass them through a block of paraffin, which is wax, and the paraffin is embedded with boron in the form of borates. It's what's known as borated paraffin. The boron atoms will actually slow the neutrons down, and once they get in here, they become thermal neutrons. And then I can do an experiment where if I took, for instance, silver 107 plus neutron, I can make silver 108, and so I can start out with a non-radioactive isotope of silver, put it in here, irradiate it with neutrons, and then I get a radioactive radionuclide out of it, silver 108. So these are, that's something that you can do. The other thing is actual, when we're talking about cross-section, it's measured in units that are called barns. And one barn equals 10 to the minus 24th square centimeters, and that's also equal to 10 to the minus 28th square meters. That's an interesting anecdote how that actually got its name, barn. It's not named after someone, but it comes from the, it's kind of a physics joke, talking about, when people say you can't hit the side of a barn. Well, these are really little tiny barns. So you figure that if you have more barns, that means you got a bigger barn. It's a little bit easier to actually hit the side of it. And when you're aiming projectiles, you want to be able to actually come in contact with the nucleus. So we've got these barns here, 10 to the minus 24th square centimeters. Anyway, when we're dealing with there's a figure 7.5. It's on page 129, and this deals with the relationship between the neutron energy and the cross section. Remember, cross section is actually giving us an estimate of the probability of a reaction taking place. So you could also call that reaction probability. So this is sigma is the Greek letter that we use for cross section, and this is in barns. But as the probability increases here, it does so as the neutron energy decreases. You'll notice that, as the neutron energy increases, you'll notice that the probability decreases. So if we start out with a cross section of 100 barns and then go down to a cross section of perhaps 20 barns, so we go like that, you'll notice that there's a pretty substantial dip. I didn't draw that as well as I might have. So if this is, let's say 100, and this next one here is 10, this is a logarithmic scale, so I don't really know where 20 would be. Maybe it's more than 20, 30, something like that. I don't know. This thing dips down like this, and it seems to be going down, and then all of a sudden you'll notice that when you get to neutron energies, this is an energy of 0.01 electron volts, and then you're at 0.10, maybe around here, 0.10 electron volts, and then you get to around 1, and then somewhere between 1 and 10, maybe at around 6 or 7, all of a sudden, so here's 1, and here's 10, and then somewhere, all of a sudden, you get this big spike. And you get another spike, you get a whole bunch of spikes after that. So this is kind of interesting. These spikes, you'd expect this, you might expect this, if this is the trend, this thing to just, continue to go like that. But every now and then, it spikes upward here. It turns out that there are certain points, certain energy integrals, where there's there's an enhanced probability of this reaction, of this capture actually taking place. And it has to do with the fact that there's going to be a certain energy where the projectile and this nucleus are actually going to be in resonance with one another. And when that happens, it's not one energy, but there's a series of energies where there's going to be certain neutron energies that are just going to be favorable for nuclear capture. And if you can hit one of those energies, then the probability, the effective nuclear cross-section actually increases very, very greatly. So even though it looks like we'd like to have very, very low energy electrons, we can neutrons, we can actually do much better with somewhat higher energy neutrons if we can match them so that there is what we call resonance capture. That is, that we can match the resonant energy of the neutron with that of the atomic nucleus. And if we're able to do that, whatever this value happens to be, let's say it's 7 electron volts, if we can slow our neutrons or find neutrons that actually have that energy, then not neutrons in this case. I think it was no. These were neutron reactions. I'm sorry. So yeah, a neutron that in that energy range would be much more likely to be captured. Maybe this one here is perhaps 12 electron volts. So we could actually design if we're going to do this reaction, we could actually find something where we could actually get neutrons that had those specific energies, and that would be a much more effective way to increase the yield of the reaction. So the yield, when we talk about these reactions running in good yield, that has to do, and I already mentioned some of these other terms. I said that one of the things that that these reactions are going to depend on, it's going to be the cross section, and it's also going to be dependent on the number of particles that we get. And we have something that's called, and also the nature of the product, but we have something that's called flux, which is the rate of particle flow per unit time. So if we have the value of the flux, and we also multiply it by the time, so it's also time dependent. So if the flux is so many neutrons per second, and then the greater the number of seconds that we run the reaction, the greater the number of neutrons we're going to actually be producing. So we can say overall that the reaction yield is going to depend on on how much target we have. It's also going to depend on the flux, the cross section, the time, and also on the nature of the product. And by nature of the product, I mean, is the product a stable product? Is the product a radioactive product that rapidly decays, or is the product a radioactive product that is going to decay over a fairly long period of time? All those things are going to make a difference.